So we've got all our angular quantities. They're just analogous. Instead of a distance along the x-axis, we have the distance around a circumference. And you divide a circumference 2 pi r by the radius, and you get some measure of angle in radians. It's really the most natural thing. And then we measure the rate of change in angle in radians per second, or the acceleration in radians per second squared. Just like we would with linear motion, it's actually really easy to change back and forth. If I want to change back and forth, I usually just multiply the r back in. Be careful that you've separated things into along the circle. It's like a tangential and linear v, and so if you want your radial component to acceleration, you still have to do the old v squared over r. Aha. But then we set up Newton's second law with torques and angular acceleration, and we come out with this mr squared. That was your rotational inertia, and it works as the inertia for rotational kinetic energy as well. Oh, is that all we did yesterday? Yeah, it is. Awesome. Okay. So on College Board's equation sheet, here's what it gives you. I want the inertia. Oh, and parallel axis. If I do this carefully, the parallel axis theorem will just show right up in the equations. Okay, so it says I equals the integral of r squared. Oh no, oh there it goes. dm, and that equals the sum of mr squareds. So actually, let's make a squiggle. That should be really self-explanatory. If we have a bunch of little point masses rotating around somehow, maybe I just want the rotational inertia of like all the little horses and rides on a merry-go-round, or maybe somehow I have this configuration of planets around the sun or something. And they're basically point masses on the scale that we're measuring. You can just add them. Each mass times its radius from the axis squared. End of story. Okay. Let me check that that's exactly what's on the equation sheet. No funny business. That's right. But oh my goodness. What is that calculus monstrosity? What's a dm? How am I supposed to integrate mass? And it's the function I'm integrating is r squared, and I'm integrating mass? What? Does that make any sense to you calculus students at all? Shouldn't r be a function of m then? Oh no. The physicists have written something very strange right there. But that's what you get. That's maybe not what I have thought of it, so we have to learn to decode that. That's your only hint from the equation sheet. And so here's how we're going to deal with that. So from calculus class, you have had some functions. We'll make it a function of time, and we'll call it v. And instead of f, bear with me. At t0, we'll start at some point v0, and it will increase in a straight line. And we're going to pick 2 points. Let's call them t1, 4. My brain's not going sideways. And t2. Okay? And so, if I calculate the integral of vt from t1 to t2 dt, I get something meaningful, right? In fact, I get the area underneath the line, or between the line and the axis, right, in between t1 and t2. You with me so far? Okay. In our physics land, this has physical meaning. If this is velocity and dt, I get delta x. I get the displacement between times 1 and time 2. Okay? Did they teach you in calculus class that dt, this dt, is actually a tiny length on this axis? And what we are doing to get the function, like you can get a function if you don't go between t1 and t2. Whoops, I should write that with more room. I'm going to scroll down, hide this rotation nonsense for now. Bigger. If I didn't put limits, I would say x of t equals v0t plus 1/2 at squared. The slope, like I have a linear up function, right? v0 plus at, there we go, we have linearly increasing function. And now I have a quadratic plus a constant that we may or may not call x0. If I started at 1, maybe it's not x0. Okay, you with me so far? When we went from a straight line increasing to quadratic, what we actually did was we sliced these guys into little strips of width dt. Did you do this in calculus, the little slices? And because you might have some crazy function, it might not be a nice physics function. And if you add up, you sum all the slices, that's what transitions your linear function into your quadratic, because, whoops, t squared, I didn't even write it, because every slice is a little bit taller than the one before it, and more and more and more. Yeah? Okay, so we smoothly transition with our polynomial from t to the first power, t to the second, and so on, because we added up little pieces, little slices of the graph. And then we fell into this habit of doing nice ones that have nicely defined functions and smooth stuff. And then if you don't have that, calculus class, you use limits and things, and you're learning the calculus tricks to analyze functions that might not be so nice. To basically sum up your math career so far. No, yes. Yes, pretty much. Okay, good. I myself taught math as well. Okay. Excellent. Then you are on your way. You are doing much better than you thought. You probably thought, oh, this is boring math that I'll never use ever. Well, in physics, we're going to use it to understand things. So let's say we have a bar. We're going to stick to one axis, good old x-axis. And we have this object, and we're going to slice an axis. It could be the y or the z direction around there, it doesn't matter. We have an axis right through the middle. Okay, we have a bar of length L, and so we have L over 2 on each side. Okay. In physics and in reality, the bar is made up of little chunks. They're called atoms, but we could imagine that they're bigger than that. And those tiny pieces we call dm. Instead of infinitesimal tiny pieces of x on x-axis, slivers of mass that make up this bigger bar, it could be a meter stick, we call them dm's. Okay. So we are going to do an integral, but we're not integrating mass. We want to do a dx or a dt integral like we always did. We use the x-axis, right? You got used to that in calculus class. It could be t, it could be x. Maybe they don't mess with you too much about that, what making the x-axis is. Okay? But these dm's, they each have inertia. Instead of just m, it's dm times x squared because we're on the x-axis. So every little piece has inertia dm times x squared, just like mr squared before. So we're doing mr squared for a point mass, just like we did the past couple days. But we have tiny ones. We got to add them all up. Okay? So then the question is, how do I put dm in terms of x? So then I can actually integrate, because I should just, if this is my 0 right here, this is my origin, I can just integrate from minus L over 2 to plus L over 2. Make that a nice 0. And then I'm good. Then I'll have the rotational inertia of the whole object, excuse me. Does that make sense? I have this I envision in physics land, this connected object, like a meter stick I'm holding in front of you, is actually all these little slivers. Oh, look, they're marked on there. I have 1,000 little slivers that make this thing up, and every sliver farther out has a little more rotational inertia. Even though it's the same mass, it's getting farther and farther out from the axis. Right? You could try this. The longer this bar is, the harder it is to rotate. You could even investigate that by holding it right by the end and trying it. It is harder, even though it's the same object. Okay, let's see how we are on time. I think we should kind of set that up. Let's define dm, and then I'll show you a couple of integrals we can do. Okay, all we're going to do is say, so we had length L, total length L for this bar, and we're going to say it has total mass big M. And this is actually not to insult you. This is if it has total mass M and total length big L, then it has a linear, okay, this is actually like a 8th or 9th grade science problem. It has a linear mass density is what physicists call it. I can't spell density, so you should not feel bad if you don't know this. How much mass is there per length of the meter stick? Sure. It's just M over L. Well, in fact, my wife is also a science teacher. She teaches middle school science, and she was just complaining to me last night how her middle school 6th graders have to know the word propagation for waves versus transmission. I have no idea. Well, that's just making it more complicated. They need to understand what waves do, not those big silly words that physicists use. Most non-physicists couldn't tell me the difference between transmission and propagation. It's fine if you can't, but if I give you a rod of mass m and length L, you better be able to tell me that the kilograms or grams per unit length is just divide them. Okay? So then here's the challenging part that people always get stuck on. What is the mass? Because you're new to calculus. It'll eventually be really obvious by the time you're taking the AP Physics test, and maybe, hopefully even by January, this will be really obvious. Okay? What is the mass of one tiny little sliver on the x-axis? This is like a trick question. It has to do with this m over L. Remember, because that's the mass per length. And then to get little masses, I need to multiply by some length. But what length do I use? Yeah, dx. Okay. That's so hard. So maybe in past years I introduced it wrong. So maybe that seems too easy. Good, if it did. Okay, but watch out. So this is a linear mass density. After break, we're going to have 2-dimensional densities or 3-dimensional densities. Youch. Oh no. And then we're going to have to integrate. We'll work up to it in 2 and 3 dimensions. Don't worry, it's not that hard. You probably haven't done that in Calc BC yet. You've not done an integral in x and y at the same time. Don't worry, you don't do it at the same time. You do one and then you do the other. And it's pretty easy. But that's it. That's dm. Oh, and I got to pause my video. And then we'll do an integral. We just multiply m over L times dx. I'll show you how.